All right, so good afternoon, everyone. So today is the lecture number 13 of our quantum computer course, right? And today, let me turn off the video to make it stable. Yeah, so today we're gonna discuss the basically the another type of qubits, the solid state and atomic qubits. And also we will talk about how we control the quantum state of a qubit, right? So last time we discussed basically, well, if we put this in like in general, we discussed the concept of a photon as a qubit for quantum communications, quantum cryptography, what we expect from a qubit, like a photon being a qubit. We discussed this concept of single photon sources and what's the difference between light bulb, laser, and single photon source, the concepts of the coherence, right? G2, G1, bunching, anti-bunching effects. Yeah, and so a photon is a good example of a bosonic qubit. Bosonic, as you of course know, bosons are particles with integer spin, right? In the case of photon, it's it relates to the polarization of a photon, and we can encode the state of a qubit in the polarization state of a photon. So today, as I said, we're gonna. So by the way, this is the chapter 5.2. So today we discuss the solid qubits, solid state, and the atomic qubits. So speaking about atoms, we can distinguish the like a general concept of an atom into two big groups. The first one is, of course, a real atom. You know, atoms are like single elementary elements that is in the heart of, or in the basis of, all materials that surround us, all materials in nature. But in addition to real atoms, we also have artificial atoms. And I put these artificial atoms in quotations. So it's not a real like atom, but a physical system, right, that consists of many atoms but behaves as an atom. So let's talk about these real atoms first, and we can distinguish two groups in terms of their quantum properties or their applications in quantum computing. So we can define atoms in the ground states. So basically, the atoms that we don't pre-populate by some excitations to excited state, but we just take the atom and select the two different states and use the atom as a two-level system. And in a few minutes we will talk about also the Rydberg's atoms. The Rydberg's atoms are the atoms that we populate first to the very excited state and then work or use the excited levels of the atom for different purposes. So the first one, atoms in the ground state. Atoms in the ground states. So if I, for example, schematically draw the energy level structure of an atom, like usually or typically it is a very complicated structure, right? So we have multiple bands. Each band consists of different sub-levels of energy, and of course, if we have an electron in the system, we can excite this electron to the excited states like this, and being excited, of course, the system can transit downward to different levels. So the system is, I mean, even a simple atom is already a complex system, and it contains many possible quantum transitions. And all these quantum transitions result in a complicated optical spectra. For example, if we consider photoluminescence from an atom, single atom or a bunch of atoms, we could detect, as a function of frequency, we could detect this spectrum like something like this, right? So multiple peaks in the spectrum, and each peak corresponds to different optical transitions in the system. And for quantum purposes, as we discussed, we need something with two states. We call this two-level system, right? So for atoms like this one, we could, for example, tune our laser. So laser typically the light source with a very narrow spectral width, so we can select, for example, two levels like this, right, and use these two levels as a two-level system. So here I zoomed out these two levels, and I can denote this level is to be, for example, the level 0, state 0, this one state 1, and yeah, so we call this two-level system, right, or a qubit, a quantum system with two well-defined states. And if we tune our excitation, our laser, to operate only within this this optical transition here, and provided that all other transitions are detuned from this main one, we can assume that in a very good approximation, these two levels would work as a two-level system. So what parameters describe this two-level system? So the main parameter is so-called dipole moment. Dipole moment. And we know, or we remember from our classes on electromagnetics or from basic physics, the dipole moment is defined as the sum over all the charges in the system times the radius vector from the coordinate origin to the position of the charge. Right. So in our case, we deal with just one electron. So the classical dipole moment in this case would be just the product of the charge times the radius vector. And if we go to quantum, as we know, we have to replace this dipole moment by its operator, right? So let's denote as D equal to E times R. So now R is the operator of radius vector, right? And as we know, so if we have an operator, we can put into correspondence the operator matrix, which would be a matrix like this ij, right? And then the inner product of some state I times the operator of the dipole moment, and then times the state j. So basically, for example, if we consider transitions from state 0 to state 1, we describe this process as by the dipole moment d01, which is state 0, then this dipole moment, state 1, something like this. So this is dipole moment of the transition between two levels. And of course, we can define this dipole moment of the state itself. It is called stationary dipole moment. Something like this, for example, for the ground state. So usually, for the vast majority of systems, atoms that we work with, the dipole moments like this one, the static dipole moment, or the dipole moment that corresponds to the level itself, is equal to 0. And the same for the dipole moment of the excited state. So we have only dipole moment for the transitional dipole moment between two different levels, not vanishing. But the dipole moment for the state itself vanishes for the vast majority of optical systems. So yeah, so this is the transition dipole moment, the main parameter that we use to describe the two-level system. An example of an atom right, that we use, like in the lab, would be, for example, atomic rubidium. Example, atomic rubidium. And maybe some of you know that one of the first lasers, optical lasers, was the red rubidium laser. So basically we use the optical transitions in the rubidium atoms for different properties. For example, to realize a laser. So these atoms are not that good for quantum applications. I mean, applications in quantum computing. For a number of reasons, and these atoms are not charged, so it's difficult to trap them, and also typically a natural atom has a small dipole moment, and also the transitions of these atoms, like rubidium atom, they the transition happen in the optical spectrum of energies, and this is not practically useful. It's better to work, I mean, in terms of computing, it's more feasible or useful to work in the microwave frequency range, in the gigahertz frequency range. And for this reason, we use these so-called Rydberg atoms. So Rydberg atoms. So it's not the elements, like chemical elements. So Rydberg here, so literally any atom can be a Rydberg atom if we excite the atom strong enough. So if we schematically draw the energy level spectrum of an atom, typically it looks like this. So we have the ground state, then at some energy we have the first excited state, then we have the third, the fourth, fifth, etc. And typically the spacing between the neighboring layers gets smaller and smaller, and for example, if initially it was in the optical frequency range, the high energy levels, they could lie in the microwave frequency range, radio frequency. Yeah, for example, if you populate your atom to the level, say, with the main quantum number of 50 or so, the energy spectrum or energy transition will happen for the microwave the energies that lie in the microwave frequency range. So if we say, if we like take a array of atoms, right, like a vessel with a bunch of atoms, then we can excite these atoms strongly to the Rydberg. So for like the states like this would be called Rydberg states. So we excite these atoms with a laser strong enough to the Rydberg states, and then this array of atoms will be sensitive to the microwave fields, the fields that cause the transition between these Rydberg states. So, for example, if you have another pulse, like microwave pulse, then this microwave pulse will cause the transitions in between the Rydberg states, and these transitions will change the properties of the system drastically. So this way you can, for example, you can detect the microwave fields, ultra weak microwave fields, and you can use the system for sensing, for different properties, purposes. So this is like an example of how we can use these Rydberg atoms, and of course we can use these transitions here as a qubit. So in order to create a system like this, we just need to excite the atom strong enough up to the high frequency states. Another point is that if you consider, for example, the energy or the state eigenstate, the state orbital of this atom, in the ground state it would be something like this, right? So I mean the size typically it's around Bohr size Rb. So it's just some size of an atom in the ground state. But when we excite the atom to the excited state, the electron cloud, right, became more expanded. So the atom effectively becomes larger, and if we excite the atom to the Rydberg state, the atom would be effectively, it would be very large. So, and if you recall that the dipole moment is proportional to the radius vector of the electron in the system, it means that the dipole moment of a Rydberg atom is very large. And since the dipole moment of the Rydberg atom is very large, it interacts strongly with any optical systems, fields, and it's like easier to control these atoms, and it's easier to achieve any optical and quantum effects. So at this point, let us change the gear and go to artificial atoms. So let me draw like a separation line here. Right, artificial atoms. So as I said, artificial atoms are physical systems. They consist of many atoms. It can consist of billions of atoms, but the system itself behaves as an atom. So it gets some energy spectrum, for example, that reminds the spectrum of a natural atom. But the main point here is that since these artificial atoms are big, we can design the energy spectrum of the artificial atom. So basically, having an artificial atom, we are not restricted by like the atom that nature provides us. We can design the properties at our will. We can design the atom. And one example of artificial atoms is so-called quantum dot. Quantum dot. So you're probably familiar with this concept. So basically, a quantum dot is just a nanoparticle or another island with a size, the characteristic size around 10 nanometers. So it's very small particle. And the material here would be like some metals and semiconductors. Like silicon, germanium, gallium arsenide, many different semiconductor materials, presumably semiconductors. So if we like zoom in the inner structure of a quantum dot, we would find the charges of two kinds. The first is the negatively charged electron. So this is electron, and a positively charged hole, right? And so one particle, so this hole, one particle is negatively charged, another one is positively charged, so we get them they interact electrostatically, right, as according to the Coulomb law. So they got this electrostatic interaction and bonding like this. So this bonded structure of electron and hole is so-called exciton. So this exciton. So as you can see, the structure with positive hole and negative electron, overall it's neutral, electrostatically neutral, consists of two particles, and the larger the interaction between hole and electron, the more the more stable this excitation called exciton. And in the energy spectrum, if I draw the energy spectrum of this quantum dot, I would get something like this. So I would get the valence band. This is valence band. This is conduction band, right? And I would have these states of the charges in the valence band. It would be holes. I draw this in blue. So I would have holes here. Let's draw just one hole. One hole here and an electron here. So basically what happens, the quantum dot can either trap the electron and hole from surrounding area, or the light excitation, for example, light excitation can cause the electron transit from the valence band to the conduction band, and due to this, the structure is very small, we have this well-defined quantum states in the structure. So we have this transition, and this transition can work as a transition in the like two-level system in an atom. But here, in contrast to a usual or natural atom, we have a large dipole moment, because the particle is, the size of the particle is 10 nanometers. So 10 nanometers comparing to the natural atom, which is roughly around 1 angstrom. So 10 nanometers is 100 times larger, roughly 100 times larger than the size of an atom. So accordingly, the dipole moment of the quantum dot is also much larger than the dipole moment of the atom. And the second point is that spectrum, the energy spectrum of this state is tuned or can be tailored at will by changing the size, material, shape, etc. So yeah, so basically you can fabricate such a structure and changing the size, the shape, the material of the structure. You will change like very accurate, in a very accurate way. You can change the this energy spectrum, and you can adjust your system to the frequency or energy of interest. And finally, the last type of qubits that I want to discuss here, let's call this Josephson Junction based. Josephson Junction based atoms or qubits, right? So let me actually take this out and put this here. So let's continue discussion here, since this is more like a big topic. So the Josephson Junction based qubits. Again, just very very briefly, like just to give you some intuition how systems like this work. And you probably know, and we already discussed, that actually the vast majority of quantum computers are based on Josephson Junction qubits, right? For example, these IBM quantum computers that we used to simulate our quantum problems, all of them use the Josephson Junction based qubits. So that's why it's so important to discuss, at least briefly, this topic here. So Josephson Junction based qubits, they operate in the RF or microwave frequency range. Which is units of gigahertz. So And in this frequency range, we can easily imagine some sort of a resonator, like for example, metallic cavity, right? So let's consider such a resonator in form of a metallic cavity. So it's just a empty box made of metal. You can imagine this like a metallic, I mean, it can be imagined like a microwave oven, right? That we use to cook food or heat up food. So just a metallic box, empty inside, and such a box, of course, supports different types of eigen modes. For example, a mode like this. So this is the fundamental mode. This is electric field. Picture and profile, electric field profile in the inside of this box, inside of this cavity resonator. And this cavity, this mode gets the resonant frequency omega. Let's denote it by 0. So omega 0. And in fact, we can describe this resonant system. We can describe the system as a lumped element approach, through the lumped element approach, as a combination of some inductance and capacitor, this L and C, right? So you know from the high school physics, if we connect two elements, inductor and capacitor, a system like this will enable a resonance, or it will get a resonance in the system. The response function would be something like this, the function of frequency. And why so? Because the capacitor stores the electric part of energy of the field, the inductor stores the magnetic part of the field, and when you connect them in a single system, you get this oscillation of the electric energy into magnetic energy and vice versa. And yeah, and at some frequency you get the resonant behavior of this. And the same happens basically in the metallic cavity. For example, for this distribution of the electric field, you would get the distribution of the magnetic field, and inside the cavity you get exchange of energy from one form to another, from electric field to magnetic field, and like back and forth in time. So yeah, so we get this resonator, LC resonator, and also we remember that the resonant frequency of this resonator is nothing but 1 over square root of LC, right? Thomson's formula for the resonant frequency of LC contour. Okay, so this is the resonator, and if you consider this resonator at the room temperature, at room temperature, this resonator already is populated by many photons, like thermal photons. And in order to get rid of them, we have to cool the system down to very low temperatures to depopulate the states. So if I schematically draw the energy of this LC resonator, it would be the energy spectrum of the harmonic oscillator. So we draw this, and it's known that the spectrum of harmonic oscillator is equidistant. So it would be a spectrum like this, and all energy gaps like this would be of the same energy, equal to h bar omega 0. So we take the resonator, we cool this resonator down to very low temperatures to wash away all the photons, the thermal photons in the system. So we get rid of all the photons in the system, and our resonator is depopulated. And then when we add one photon to the system, we get our system to this point, to this level. If we add another photon to the system, we jump up to the second state. If we add third photon, we promote our system to the third state, fourth state, and so on. So this system basically can be populated by as many photons as we want. Does it work as a two-level system? No, because we need to isolate just one transition in the system. So we have to somehow change this spacing between the levels to make it unharmonic, to make these transitions like different, so we can select just two levels in the system. So we need to bring some nonlinearity, and how we do so? We bring this nonlinearity via the Josephson Junction effect, or Josephson Junction Josephson effect. Let's write this here. Josephson Junction. Josephson Junction. So what is a Josephson Junction? Let's consider, so I didn't mention it here, but the fact that we cool down the resonator to get rid of the all noise thermal photons means that we cool down the system very well below the critical temperature of superconductivity. So basically, since our resonator is metallic, we cool this resonator down to very low temperatures, typically at like tens of millikelvin. So it's almost fundamental zero temperature, right? In this regime, we depopulate the resonator, so it doesn't contain any excitations. And at this frequency, many metals, they became superconductive. Not all of them, but many. For example, aluminum, which is not good conductor at room temperature, becomes superconductor at low temperatures, the cryogenic temperatures. But in contrast, metals like copper or gold, silver, they don't turn into superconductive state. So some materials became superconductive, some materials don't. So if you take like two metals made of superconductors, like here I took one, and here I put the second one, and these two metallic parts, wires, they form the junction with a layer of dielectric inside between them. So this is dielectric. Dielectric means doesn't conduct electricity, right? So no current through. And and metals, the superconductors, of course, they have a bunch of electrons, and if you apply electric bias across this junction, these electrons would run to this left side, but because of this dielectric, they can't go through and jump to the second superconductor. But this works for electrons when they are in the fermionic state. Today we have this theory, Bardeen-Cooper Bardeen-Cooper-Schrieffer the theory that tells us that below the critical superconductivity temperature, the electrons can actually couple to each other to form so-called Cooper pairs. So let me draw this schematically like this. So for example, if I have two electrons, even though they have the same sign, right? They both negative. So this interaction cannot be because of the electrostatic interaction. This is actually due to the interaction of electrons through the crystal structure. In the at the microscopic level, you can imagine this something like this. So suppose you have this metal with this crystalline structure like this, right? And then you have one electron that goes through this crystalline structure, and you have another electron, for example, here. It also runs in this direction. So these electrons, they repulse each other because they both negatively charged, but at the same time, this crystal structure, these atoms, they get positive charge, and this electron just slightly attracts these atoms while it goes through the structure like this, and effectively this area becomes like positively charged, and this presence of electron polarizes the crystal structure of the metal. So in this local area around this electron, this area becomes positively charged. This area around electron, positively charged area, interact with this electron, with this first electron, and it creates this Cooper pair. Cooper pair. So the Cooper pair is a combination of at least two electrons. So the electron is a fermion, as you of course know, a particle with 1/2 spin, right? The half integer spin, mainly, namely 1/2, and the system of two electrons, this Cooper pair, forms another type of quasi-particle called Cooper pair, and this Cooper pair is a boson because spin 1/2 of first electron plus spin 1/2 of the second one gives you 1. So the Cooper pair gets the spin 1. So the Cooper pair is a boson. For the boson, for the boson particles, we have another type of statistics, and the very important fact about bosons is that due to their their integer valued spin, they can form, they can condense in the boson-Einstein condensate. So it's like difficult to follow, to understand, but the logic is pretty simple. So let me draw this down here. So Cooper pairs are bosons. Spin is equal to 1, right? So Cooper pairs can form a condensate, so they can form condensate to the single quantum state called Bose-Einstein condensate. You're probably not aware of this, but you deal with Bose-Einstein condensates like very often, maybe every day. For example, a laser is an optical system, right? It gets these photons as excitations. A photon is a boson. A photon has exactly the same spin of 1. And basically when you turn on your laser, like for example laser pointer, what happens is that photons, because of some physics, right, some internal physics, all the photons they they come to the same quantum state. So the same quantum state means that all photons have the same frequency, energy, the same polarization, the same direction of propagation, and this is exactly why a laser forms such a very directive beam. So the fact that a laser shines light in a very narrow light beam is a consequence of the fact that a laser forms this Bose-Einstein condensate. So basically all photons are in the same quantum state. So in this Josephson Junction effect, a similar thing happens to Cooper pairs. So the electrons, they interact through the crystal structure of the metals, and they form Cooper pairs. And as they form Cooper pairs, the gas of Cooper pairs, the Cooper pairs condense in the Bose-Einstein condensate. And in this Bose-Einstein condensate, the whole system, the whole gas of electrons behaves as a as a single wave or like quantum wave of state quantum state psi. So when Cooper pairs condense in the single state, they form a wave, and this wave can propagate through the dielectric, this dielectric layer between. So by the way, this dielectric layer, the thickness of the dielectric layer is like around from 1 to 5 nanometers. So it's very thin layer of dielectric. But without this condensation, this dielectric doesn't allow to current go through. But in this quantum state of Bose condensation of the Cooper pairs, they form a quantum wave. All the particles in the system, they form this quantum wave, and this quantum wave can tunnel through this barrier. So this is a illustrative picture how you can describe this Cooper, this Josephson effect. So why we bring this effect to the description? We bring this effect because this effect is actually nonlinear. So if we consider, if we apply the electric bias to this junction and now vary this bias, this voltage, right? This voltage drop across the the junction, and measure current. So we represent this result in a IU current voltage diagram, right? We would get something like, something like this. I mean, very schematically. So it will get like a linear part of the characteristic and then very nonlinear part. And the important point about this characteristic is that this nonlinearity happens at the single photon level. So if this junction absorbs one photon, it generates some no, it's wrong to say this way. If we get if this junction gets a portion of a current with energy that corresponds to the energy of one absorbed photon, you get nonlinearity in the system.
Alex, I have a question right now.
Yes.
So what I understood is, like, for example, if I have a n-qubit system, and eventually with some computation, if all my states are at one, so is that a laser because how it is behaving? That's what you mean?
So if you have a number of qubits and all the qubits are in the ground state, is it condensation or not? Very good question, because so if you have a number of qubits, like n qubits, you, of course, if the qubits are strongly coupled, you describe them using one single state vector, and in their ground state, they all like condense to the ground, to the zero energy. I mean, it behaves as a like it reminds a condensation, but it is like a matter of state. The condensate is rather about a matter, right? So when you have like electrons that condensate to the single state, or photons that condensate to the single state, zero state of a number of qubits, it looks like a condensation, but it doesn't relate to the like real matter. So this way, I would say it is like similar, but I wouldn't call this a condensation, you know. So, but yeah, the question is very good. Yeah, so this Josephson Junction is nonlinear system. Why we need it? Because if we add this Josephson Junction, so by the way, the graphical representation on electric or electronic schemes, this Josephson Junction element is represented by this graphic sign, or like a box with cross inside, something like this. So this is Josephson Junction schemes. So if I put this Josephson Junction in my resonator, like here, for example, I make this resonator nonlinear. And this nonlinearity makes the energy spectrum of the Josephson Junction, based resonator, unharmonic. So let me draw again this harmonic spectrum by dashed curve. Right. So this is perfect harmonic oscillator energy dispersion. But when we put this Josephson Junction, our energy spectrum, the energy spectrum of the system behaves like depends like this. So this is the new dispersion of energy spectrum, and due to this unharmonicity, the energy levels of this resonator become non unharmonic, non-equidistant. So, for example, this state 0, 1, 2, the frequency transition 0, 1 is not equal to frequency transition 1, 2, and does not equal to frequency transition 2, 3, etc. So you get these different frequency of energy transitions. And again, this allows us to select these levels, for example, these two fundamental levels, and use them for two-level system, right? Or a qubit. So this is the fundamental principle how these Josephson Junction based qubits operate. There are different types of Josephson Junction based qubits, but like the main point is like this. And as I said, the vast majority of the quantum computers that exist today, including those IBM quantum computers, all of them use this architecture of Josephson Junction based qubits. So it's pretty important to have an idea how these things work at the level of single elements. So let me write this. So IBM quantum computers are based on this approach. Yeah, so sometimes we call this quantum circuits or quantum RLC circuits. Quantum RLC circuits. Very good. So do you have any questions regarding this part about the qubits?
No.
All right. So then now let me let us discuss the control of the qubits. So how do we control a qubit? How do we control a qubit? And for example, if talking about this quantum superposition, right? How we create a superposition having a qubit. So as we discussed, the one of the most important parameters of any qubit, I mean not any, most of them, of most of the qubits is the dipole moment, and the existence of this dipole moment means that the qubit is sensitive to the electromagnetic field. So this dipole moment can be electric and magnetic, and sometimes we use these magnetic qubits. They controlled by magnetic fields, but the most of them are electric qubits, so they sensitive to electric field. So if my qubit has a electric dipole moment, then when I apply the electric field, this qubit gets extra energy, right? The energy of interaction of this dipole moment with the electromagnetic field, with the electric field, like this. So from the classical physics, we know that this energy of interaction is minus dipole moment times electric field, and minus because this system gets the minimum energy when the dipole moment is directed in the opposite direction from the electric field. So basically the dipole tries to get the orientation in the opposite direction from the electric field. So this is the energy that the qubit, any of these electric qubits, gets in the electromagnetic field. And the electromagnetic field, of course, can be a function of time, and accordingly, this energy will be the function of time, right? So I applied like a pulse, and due to the interaction, this interaction energy will be also the function of time. So now let me describe. Let me consider like a generic qubit. So it's a system with two states. We call this state 0. This is state 1. And without electromagnetic field, the system gets the Hamiltonian sub-zero. Right, so this is the intrinsic Hamiltonian of the qubit as a system. It describes the energy spectrum of this qubit, etc. But when we apply electric field, it gets this second term U, and in quantum it is a operator, and let's call this the total Hamiltonian of our system, of our qubit. The the intrinsic Hamiltonian, by definition, right, it is, I mean, according to the equation for the eigenstates and eigenvalues, right? So these states 0 and states 1, state 1, they are eigenstates of this intrinsic Hamiltonian. So let me write this this way. So when my intrinsic Hamiltonian acts on this eigenstate, it creates nothing but the energy of this state I times this state, the state itself. And the state I is just the either state 0 or state 1, basically this state or this one. And the energy I is, in terms of frequency, it is h bar omega I. Right, so for example, the energy of 0 state, it is h bar omega 0, A1, it is h bar omega 1. Yeah, and we also denote this transition energy, transition frequency, omega 0, 1. So this is the, I mean, in terms of energy, it is h bar omega 1 minus h bar omega 0. So basically this energy, omega 0, 1. Right, so let's describe the behavior of this qubit in the electromagnetic field. How we do so, you recall from our first part of our course, we bring this time domain Schrödinger equation, which is I h bar d psi over dt, and it's equal to the total Hamiltonian times psi. Here I don't use this Dirac notation, so I just write psi instead of ket or bra psi vector. I mean, for simplicity. What is our psi here? So first of all, this psi will be a function of time, of course. and it is equal to basically the probability amplitude of finding the system in the state 0. Now it will be the function of time, and times this 0 state, right? Eigenstate, then plus state 1 t and state substate 1. Or we can explicitly rewrite this, replacing this state 0, state 1 by like a real functions that describe the coordinate part, the special part of the psi vector of the state, and the harmonic part of the state. So it will be c sub 0 t, and then I write the special part by phi sub 0, and then the harmonic part to be e to the power of minus I omega 0 t. Right. So from the first part of the course, you supposed to remember that the solution to the steady state Schrödinger equation. Steady state means no field applied, so our system in its steady state, so we don't have this time time dependence, and in the steady state the solution is multiplied by this this harmonic function. So this is the first term, and of course plus the second one for the state 1. So again, this probability amplitude times phi 1 e to the power of minus e omega 1 t. So this is our general state of a qubit, and our task is to find these coefficients. So basically how these coefficients change in time when we apply electromagnetic field of some form. All right, so now we can put this, instead of putting this to the Schrödinger equation, let me take the time derivative of this function. All right. So let me write this step by step. So I have the c sub 0, then phi 0 e to the power of minus e omega t, then plus c1 phi 1 phi 1 phi 1 e to the power of minus e phi 1 t. So this time derivative, of course, acts on the c coefficients, right? They depend on time, and also this harmonic coefficient that also depends on time. So what we get here, we get c sub 0 dot corresponds to the time derivative, right? So this Newton notation, Newton notation for the time derivative. So the first term is then phi sub 0 e minus e omega 0 t, and then plus second term, which comes from the time derivative of the harmonic function. So it is c sub 0 phi 0 minus e omega 0, all right, and then e to the power of omega t omega 0 t, and the same for the second term. So we get c1 time derivative phi1 e to the power of minus e omega 1 t, and then plus plus c1 phi1 minus e omega 1 e to the power of minus e omega 1 t. Okay, so now I can group these terms like this one and this one and these two by factorizing the factorizing this the special part of this and the harmonic term part of in each term. So what I get I get c sub 0 dot minus e omega 0 c sub 0 phi 0 e to the power of minus I omega 0 t, and plus second term c1 dot minus e omega 1 c1, then phi 1 e to the power of minus e omega 1 t. So this is for the time derivative of this generic c function. So now we can plug in this to the Schrödinger equation, to this one, to the Schrödinger equation. What we get? We get I h bar, right? This term prefactor here. Then our function that time derivative of the psi vector that we just obtained. So it is c sub 0 dot minus e omega 0 c sub 0, then phi 0 e to the power of e minus e omega 0 t, then plus c1 dot minus e omega 1 c1, then phi 1 e to the power of minus e omega 1 t. Oops, let me move this down a little. Okay, and it's equal to, so for the Hamiltonian, I write this as a sum of two, the intrinsic plus the interaction, right? And then for the state vector, I have this one, this general vector. So it is c sub 0 phi 0 e to the power of minus e omega 0 t plus c1 phi 1 e to the power of minus e omega 1 t, this way. So now I look at this operation here, h, the Hamiltonian of intrinsic acting on this phi sub 0. So if I consider this term, what I would get, this is nothing but the steady state Schrödinger equation for the state psi 0. And by definition, it's equal to h bar omega 0 phi sub 0. And the same for the state 1. State 1, I will get omega 1 phi 1. Right? And now if I consider, I mean, for example, this state, when I act my the Hamiltonian of the intrinsic Hamiltonian on this part, I will get h bar omega 0, then c sub 0 phi sub 0 e. I will get exactly this part, but with the opposite sign, right? So if I multiply this imaginary unit here and also h, I will get plus h bar omega sub 0, c sub 0, phi sub 0, e to the power of minus I omega 0 t. So these two terms will cancel out on both sides. And my equation will be significantly simplified from this. So what I get, I'll get imaginary unit h bar, then c sub 0 dot, phi sub 0 e to the power of minus I omega 0 t, then plus ah bar c sub 1 dot phi 1 e to the power of minus I omega 1 t, and it's equal to basically this product of interaction part of the Hamiltonian with these two, so it will be c sub 0, then u, then phi sub 0 e to the power of minus I omega 0 t, and then plus sub 1 u operator phi 1 e to the power of minus a omega 1 t. Very good. So what we can do now, we can just deuse the fact that the phi sub 0 and phi sub 1 are orthogonal, which means that if I take the integral like phi sub 0, phi sub 1 complex conjugated r, it will be equal to 0. So all all the inner products like this will cancel out. So I can multiply my equation by first phi sub 0 complex conjugated, and then integrate over the entire space, and then I can multiply the same one by phi sub 1 complex conjugated, and again integrate over all the space. So this way I will get the system of two coupled equations. And also when I multiply, for example, this part here by this phi sub 0 and then integration, it will give me the matrix element like this one, right? So it will be phi sub 0, then u, then phi sub 0. So this matrix element for the Hamiltonian, for the interaction Hamiltonian of the qubit. And the same way I will get these elements u01, for example, it will be phi 0 u, phi 1, and etc. So four elements. So the result, let's write down the result. So for the c sub 0 dot, the function of time, I will get minus I h bar, and then c sub 0 t times u double 0 plus c sub 1 t u01 times e to the power of minus e omega 01 t, and the second one c sub 1 dot t minus a h c sub 1 t u c sub 1 t u double 1 plus c sub 0 t u 10 e to the power of minus plus I omega 01 t. yeah, two two equations. So now at this point, I recall that my the interaction Hamiltonian is equal to minus d times e, right? And I assume that my electric field is a cosine function. So I have this amplitude with polarization and cosine omega t. So now I use the Euler's formula to represent cosine as the sum of two exponential functions. So I get e sub 0 over 2, and then e to the power of I omega t plus e to the power of minus e omega t. All right, so this is the just representation of the harmonic field. So now, yeah, and of course this omega is the excitation frequency. So this is a new frequency, right? This is the frequency of the excitation pulse that I use to excite the system, like a excitation of a laser beam or excitation of microwave field that I apply to my qubit. All right, so then the matrix element like this one, uij, right? This matrix element, so I have to put this the equation for the Hamiltonian interaction Hamiltonian to this to this matrix elements. So I'll get what? I'll get the phi u phi j, right? So the amplitude is a constant. I take it out from the integral. The exponential functions also don't depend on the coordinate. So I'll get this matrix element d ij I0 over 2, then e to the power of I omega t plus e to the power of minus e omega t. And dij is this phi I d phi j. So as we already said, d00 and d11 usually equal to 0. So I just omit these two terms, and I plug in this equation for the interaction Hamiltonian to these two equations here. And at this point, we can also introduce this very important quantity, which is called Rabi frequency. It's equal to d01 e0 over 2. Oh, sorry, over h bar. So this is Rabi frequency, and if I multiply this by h bar, I will get Rabi energy, right? So the Rabi energy would be equal to the product of the dipole moment and the amplitude of the electric field. So this is Rabi energy. So Rabi frequency and Rabi energy, very important parameter. It gets two elements, right? Two entity, dipole moment of the qubit, which describes the qubit itself, and the electric field amplitude, which describes the electromagnetic field. And the Rabi frequency or Rabi energy is a quantity that describes the interaction of a qubit with the electromagnetic field. Basically, the larger the Rabi energy, the stronger the interaction of the qubit and the electromagnetic field. And in theory, in experiment, we describe these interactions only in terms of Rabi energy. So introducing this Rabi energy here and taking into account that the diagonal components of the dipole moment are equal to 0, and plugging this Hamiltonian to these two equations, right? We get the following almost final results. So it is C sub 0 dot is equal to imaginary unit Rabi frequency over 2, then the parenthesis e to the power of I omega minus omega 0 1 t, then plus I to the power of minus I omega plus omega 0 1 t and times c sub 1, and the same for the second one up to the change of the index. T to the power of minus e omega minus omega 1 t, then plus e to the power of I omega plus omega 1 t times c sub 0. Okay, these two equations. So these two equations is a nice point to introduce this rotating wave approximation. So rotating wave approximation is a very popular type of approximation. You can meet it in tons of literature on quantum optics, quantum mechanics, computing, etc. So what this is about? So rotating wave approximation. So rotating wave approximation, or RVA, it basically consists in neglecting the fast oscillating terms in the equations. So the system of equations must be solved together, right? These two equations are connected. We have the first one is the equation for the C sub 0 through the state sub C sub 1, but in the same time C sub 1 is defined by this second equation, differential equation, which also depends on the state of C sub 0. So these two equations are connected and have to be signed. These have to be solved like simultaneously, and this is a very difficult problem and can be solved analytically in an analytical way. But if we consider only the slow dynamics of these two solutions, which means if we assume that the excitation frequency is very close to the resonant transition frequency, right? What it means? It means that the function e to the power of I omega minus omega 0,1 times t, it will be slow or fast function. It will be a slow function because the difference between omega and omega 0,1 will be very small, so it will be slow. It will be slow. But at the same time, if you consider the second the second term, like e to the power of I plus omega 0,1 t. So the closer to the resonance, it will be like fast, at least much faster function than the first one. And if we could solve these two equations, we would get the dynamics like slow dynamics and filled with this fast dynamics. So usually we are interested in this slow part of the dynamics, so we can omit the fast oscillating parts. So we can omit these two terms, which oscillate or change much faster than the first two. So in this rotating wave approximation in RVA, we get these two equations in a much simpler form. So for the C sub 0, we'll get I omega R Rabi energy over Rabi frequency over 2 e to the power of I omega minus omega 0,1 t C sub 1 t, and the second one for the second state, C sub 1 t equal to I omega R over 2 e to the power of minus I omega minus omega 0,1 t C sub 0 t. So these two are final equations. These equations define or describe the dynamics of a qubit in an electromagnetic field. The field itself, the electromagnetic field strength enters the Rabi frequency. So this Rabi frequency is a function of time and also a function of amplitude of the field, dipole moment of the qubit, right? We can simplify these two equations even further, assuming that we have exactly resonant case when our excitation exactly at the transition frequency of the qubit. So in this case, these two equations simplify to C sub 0 equals to I omega R over 2 C sub 1 and C sub 1 I omega R over 2 C sub 0. Very like two equations. And now if I take the time derivative of both and then plugging the second one to the first one and vice versa, I'll get very simple result. So it will be C sub 0 double dot, then plus omega r squared over 4 C sub 0 equal to 0, and the second one in the same way, omega r squared over 4 C sub 1, 0. So basically two identical equations, second order differential equations with this term, which is obviously the frequency, right? So we got the oscillations, and we call them Rabi oscillations, Rabi oscillations. I mean, you probably remember this like from mechanics or electrical engineering, or I mean whatever. This very simple second order differential equation, like amplitude second order differential of amplitude times omega 0 squared a equal to 0, right? So the solution of this is just sine or cosine and harmonic oscillations. So the same way we find these solutions to these two, and let me write them in red. So the solution of the first one will be C sub 0 t is equal to cosine omega r over 2 t. And solution for the second one we can write through sine. So let's write this imaginary unit, sine omega r over 2t. And so this is for the probability amplitudes. And if I take the modulus square, I will get the probabilities itself, right? Or population. So population of the first state, it is cosine squared omega r over 2t, and population of the second state, it will be sine squared over omega r over 2t. So these two solutions for the populations of the states, they are time dependent, right? They depend on time, and obviously they represent oscillations. So if I plot these two as a function of time, let me plot this as a function of time. Here is population, either first or the second state. And in different colors, let me start from the population of the ground state. So it will be a function like this. So this cosine squared function. And for the second state, I assume, so here I assume that my qubit at the initial time moment t0 is in the ground state, right? And then I apply electric field, and the system starts oscillating like this. So initially my excited state in the population 0, but as time changes, it goes to 1, then goes to 0, then goes to 1, then goes to 0, and something like this. So this c sub 1 squared, and this one is c sub 0 squared. Population of the ground state and excited state. So again, what it means that if I take my qubit two-level system, right, with states 0, state 1, I apply like electric field to the system. It's a function of time. So in this system, if it's like was initially in the ground state, in this system I get the oscillations of population of this ground state and excited state. So it constantly, these two levels, they exchange the electron. Basically, it starts from the ground state, then goes up to the excited state, then goes down to the ground state, and I have these oscillations. But what if the electric field is pulsed? So if electric field is pulsed, then the Rabi frequency is also pulsed. If ET is pulsed, then omega R is also pulsed. Right. And if omega R is pulsed, then I can change the duration of this pulse in order to prepare my qubit in a different state. And there are two important cases here. So the first one, let's call this pi pulse. Pi pulse. For the pi pulse, I excite my system by a pulse with a duration t that equals to pi over omega r. So if I go up to these equations and put t to be equal to pi over omega r, I will get cosine squared of pi over 2, which gives me 0. And for the sine, I will get 1. So at this diagram, where is this pi pulse? It is here, right? So this is the pi pulse. So I had a qubit in my, the qubit in the ground state, and I prepare this pi pulse. I send to the qubit, and after the pulse like passed through the qubit, the pulse prepared the qubit in the excited state. So it enables or causes transition from 0 state to state 1. So it is the physical realization of the sigma X gate, or bit flip gate, right? I had gate in one state, I sent the pulse, and the pulse, this p pulse created, flipped the qubit. If then I sent another pulse also with pi duration, it will change my qubit from state 1 to state 0. So this sequence of pi pulses enables this sigma X gate. The second,
I have a question.
Yes.
So this pi pulse is the same as the continuous wave pulse. The way that is what the continuous wave pulse does, right? When you give to a ground state, it goes to one, and vice versa.
No, this is not continuous. This is actually pulse. So this pulse must have a duration of, equal to pi over omega r. So it is a really like a pulse. It should be like a pulse like this.
But they're doing the same function, right? They're making the transition, whether it be the pulse or a continuous wave. The function of both are same, right?
No, so the function of the continuous wave is basically, shown by this this time dependence the plot. So if you apply a continuous wave, just like a continuous wave, right, then your qubit will transit from the state 1 to state 0, then back to state 1, then state 0, state 1. So it will oscillate in time. And this is the Rabi oscillations. So in order to like prepare the qubit in a particular state, you have to stop your excitation at some point. So and you can stop your excitation at different time moment, and this will leave your qubit in different state. So this is about pi pulse. And the second type of pulse is so-called pi over 2 pulse. So in this case, the time duration of the pulse is equal to pi over 2 omega r. Again, if I put it here, I will get cosine 1, sine for sine 0. So, oops, no, I will get 1/2 here and 1/2 for the first one and for the second one. So my this point will be here. So this is the pi over 2 pulse, when the probabilities are, or populations are, the same and equal to 1/2. So in this case, what happens is the transition from the ground state to the state 1 over square root of 2, 0 state plus 1 state. And this is nothing but the state plus, and the pi over 2 pulse enables the Hadamard gate, H gate, right? So this sigma X gate, Hadamard gate, and other types of gates are enabled just by the pulse engineering. So basically you send the pulse of different duration to your system, and this enables this gate operations. Pretty simple. At least for single qubit gates. Yeah, and in general, for the pulse of arbitrary duration, we would write the state of a qubit in this way, right? So this is in the general state, and through these solutions that we just obtained, the first one will be cosine omega r over 2t times 0 state plus I sine omega r over 2t state 1. So you just change the pulse duration and the pulse like electric field amplitude and the dipole moment of your qubit. So you basically do this pulse engineering, and this way you can achieve different operations, the quantum gates, right? So at least for the qubits that we just discussed, this works this way. Yeah, unfortunately, I don't have time to discuss the entanglement. So basically, this way we can also describe the entanglement. Physically, this is just the strong coupling of two qubits, and the 2-qubit gates, like C0 gate, for example, that we used in quantum simulations, right? The realization is a similar, but in contrast to single qubit operations where we can have just one laser or one excitation, for the 2-qubit gates we need two frequencies. So basically we excite the system of 2 qubits using 2 waves of slightly different frequencies, and basically manipulate them the same way. This is like physically how all this works. And finally, yeah, do you have any questions regarding this part?
No.
All right, and then the last part, I mean, I just want to mention this for completeness of the story. Chapter 5.4, let's call this damping. And decoherence. Just to give you an idea what is damping and what is decoherence. So what we just discussed is so-called ideal lossless case, which is never realized in reality. So this is no loss, no noise, no loss, no noise, perfect system, never found in nature. All right, so what we just discussed at this picture, we say that if we have a qubit, we excite this qubit by a wave. It will behave like this and then oscillate somehow. But if we stop our excitation, for example, at this moment, our qubit will be trapped in this state like forever. Without any loss, any state of a qubit is a steady state without loss. So if I stop my excitation of the qubit, it will be trapped in this state. But of course, it doesn't work like this in reality. In reality, when I stop the excitation, then the qubit will decay somehow to the to the ground state. Right. So let's briefly consider the real case. Loss and noise. Loss and noise. So in the real case, again, if I have two-level system, I can excite the system to the excited state, for example, using this pi pulse, right? And then my pulse is gone, and I leave this system for its own. And what happens in reality, right? We know this from like very well. So it gets decay. So basically, the system from the excited state, it transits to the ground state, and the characteristic time that requires the system to decay from excited state to the ground state is called this T1. So T1 is a decay time, and the fact that the system transits from the excited state to the ground state means that the system loses the energy. So this T1 basically is the time at which the system decays in energy. Energy decay time. T1 energy decay time. Energy decay time. Like if you have a pendulum, you swing the pendulum, it oscillates, but after some number of oscillations, it decays. So it almost don't oscillate, and this is the time of energy decay time. So this is the T1. But in contrast to classical physics, where we have this energy, right, we also have the wave nature of quantum states, and the wave gets this important property of coherence, right? And the fact that and the quantum system in the reality can lose this coherence in form of dephasing. So for example, if you have a quantum system like this, let's suppose your system in the ground state, you can excite a system with a non-resonant wave, and this electron will start oscillate around the atom, around the system, like this, and it will oscillate in time like this. And if your atom in the excited state, again, you can excite it, and it will like oscillate and decay like this, being in the excited state or in the ground state. And this process is described by this parameter T2, and T2 is the dephasing. Dephasing time. And yeah, T2 is the time of losing the coherence, right? Time of dephasing. And this is like pretty important to understand that a quantum system, of course, it can be like it can do transitions between different quantum states, but on top of that, and this is like more important, is this decoherence time. So usually decoherence time is shorter and even much shorter than the decay time, and all the quantum physics or like entanglement, superposition, it's all about dephasing time. So in practice, we need to increase this dephasing time as much as we can. At this moment, let me make a little break, and I will be right back in a few minutes. All right. What was I? Yeah, this time, decoherence time. So energy decay time phase decay time. And typically T2 is shorter or even much shorter than the energy decay time. And if we're talking about these Josephson junctions, for example, like a good qubit is said to have this decoherence time around 100 millisecond. So a qubit with a dephasing time 100 millisecond is already a good qubit. And why it's so important? It's important because basically your quantum algorithm cannot run longer than the characteristic decay time, dephasing time of your circuit, right? So basically, yeah, a quantum computer is something that runs very quick, 100 millisecond, so it's much shorter than a second. But since this this electronics, this quantum electronics works at the high frequencies or high speeds, then 100 millisecond is already enough to do some simple quantum algorithms, execute quantum algorithms. So and also at this point, people also discuss this gate time. So the gate time is a characteristic time that needs a qubit needs to do the operations. For example, for this case that we just discussed, this, for example, pi over 2 pulse that enables this Hadamard gate, right? So this gate time would be around pi over 2. Time duration, which of course depends on the Rabi frequency, dipole moment, electric field. So gate time, the time that a qubit requires to perform the operation. And of course, we require a good, we need a good qubit to have gate time much shorter than the decoherence time. So for a good qubit, decoherence time must be much larger than the gate time. So we can do multiple quantum operations before the phase decays. All right, so this is basically end of today's lecture. Do you have any questions regarding this part?
Yes, I have a question.
Okay.
You explained two types, like energy decay time and phase decay time.
Yeah.
So as I can see from the image, like energy decay time, so that's also a problematic thing, right? Because for example, for a gate where we just want it to reach 1 and don't want the value to go to ground level, we have to perform all the operations before it goes to the ground level, right?
Yeah. So yeah, of course, T1 is also like a problem. We also need T1 as larger as possible. The point is that quite often, or I mean, as a rule, T2 is smaller than T1. It's because simply due to the fact that in order to decay in energy, like first your phase decays and then your system decays in energy, or while your energy decays from the excited state to the ground state, of course you lose the information about the phase. So T1 is always larger than T2. That's why like people worry more about the T2 rather than T1. And also T1 can be improved like in different way. For example, you can couple this qubit to a high quality factor resonator, which increases this T1 like very much due to the interaction with the high quality factor cavity. You can make a system with large T1, but this way you can't increase T2. So your T2 is limited or restricted by some internal processes like Cooper pair, breaking, some maybe noise, thermal noise, many factors there. So that's why like we care more about dephasing time. But T1 is also important, of course.
Okay.
Do you have any other? All right, then, yeah, thank you very much. Let me stop the recording at this moment, and we can discuss the formal things if you have any.